also the only thing I could think of was just that the range of G needs to lie in F's domain.
So here the range of G needs to lie in the domain of F, but not be equal to B.
So can you hear, guys? I'm using a new microphone, so I'm not sure if it works. Do you hear me?
So the point is,
yes.
All right.
Then this rule here can get messed up. So I guess an example of this would be.
So let's give these people 2 minutes and see if they leave the room voluntarily or I have to kick them out.
Yeah, 2 minutes. So if we do the same, it's mathematics, we're allowed. Let's see. So if I do the same guy here, like this, and then now I make a really stupid choice for G. I take G to be the function who is 1 for all x.
I'll just start working out this integral, all right? Without talking.
Now, certainly at Lund, x goes to 1, I guess. Let's do 0 versus Lund. Right. And is equal to 1.
Yeah.
1. But then x equals to 0, f g x.
Right, so that's the integral, and then the domain D here is just x bigger than 1 and y bigger than 1. So if I do partial integration, I just integrate from 1 to infinity with both of them, right? So that's pretty straightforward. So you have 1, infinity, 1, infinity. This is 4.
We're really now into the final rate.
Then here you see that.
This is a stupid example. No one will
Okay, so x is the inner derivative of this guy, and y is the inner derivative of that guy. So
Yeah, but yeah.
What you can do is just well, take a picture. I as a 5 dash or 5. Then just apply this to it. Then it will be wrong. Then this will be false. This works. This doesn't work. And we get no points.
there's a crucial point. The first integral, the one with respect to x, where is it? There. This we can solve because x upstairs is the inner derivative of x squared downstairs. Let me fix the zoom.
So is it possible if I could talk to you like
So you can follow me to my office then if you want, or
yeah, that would be good.
let's just find
Are you going to do it now or sometime later?
we can do it sometime.
All right, but then for the other guy here,
No, I would assume that you
Yeah,
want to do it or something.
2y is the derivative of y squared. So if we integrate with respect to x, I'm not saying it's not something we can compute, but it's certainly something which is difficult to compute, right? Because we don't have that inner derivative. So what I will do is I will switch the order because partial integration, you can always choose which one you do first. So we get an easier integral if we do this. But now, okay, so here I put the 2 and then I put the 1/2 in front just to have the inner derivative here. And now we can kind of see what is the primitive.
So in another?
right? So with a bit of habit of solving these kind of things, you see that if you differentiate this guy, the -1 kills the minus. You get a -2 here, which is that guy, and then the 2x comes from the inner derivative. Okay, so it's that from 1 to infinity, and then there's a dy outside. And similarly here, right? And from here on, it's just pure computation. So this was, I guess, the thing we wanted to test here, that you kind of know how to do partial integration one way or the other way, depending on what works out best. So the rest here is just computation, right? So what we get here now is 1/2. Then at infinity, this evaluates to 0. So technically we do a limit, right? We write here a big R, and then take the limit as R goes to infinity. But, okay, so at the end of the day, we have x squared, sorry, 1 plus y squared dy minus, and then here we get the same thing, integral 1 to infinity, 1 plus x squared dx. And of course, now x and y are just dummy variables, so I could replace both of them with a t. And then this is minus 1/2 integral from 1 to infinity. That it's the same integral here, despite x and y being, these are just dummy variables. They don't carry much meaning. Right, so at the end of the day, we know that arc tangents is the primitive here. So in the limit, as t goes to infinity, arc tangents of t is pi/2, and at the value when is arc tangents equal to 1/2? So tangents of 30 degrees so one of them is a half, and the other one is a square root 3. That's also the no arc tangents of 1/2. Okay, so I don't think arc tangents of 1/2 is one of these numbers we're supposed to know. Anyways, this is a correct answer, so I mean, it's fine like that, right? Yes, questions? Okay, moving on to B, so 4B, let's have a look at it. It's exactly the same integral. It's just that the order of, the domain is different. So the domain looks, so here, modulus, I should have written here norm. So modulus of xy, that's the same as the norm of xy. What's going on here with the questions? When I share and somebody writes a question, I don't know why, but I can't see it. I'll just pause share and then. Well, arctangents of 1 would be pi/2, but why is it arctangents of 1? Because I'm integrating from 1 to infinity. Yeah, you're right. I was surprised. I don't know. I jumped too many steps. Okay, so this is arctangents of t. Of course, it's a 1 here, so yeah, screw that. sorry about that. So at the end of the day, it's pi divided, so it's pi over 8. Well, even masters make mistakes sometimes. So now doing the same computation for this other domain, which is just the radius being bigger than square root of 2, we need to switch to polar coordinates, right? So for B would be double integral radius bigger than square root 2. So this is like a set, a bit sloppy notation. And then we have our integrals the same, so r cosine theta minus 2 or sinus theta divided with r to the power of 4, right? Because this x squared plus y squared, that's an r square, and then there's a square on that as well. So, and then the theta, the r, so this is supposed to be interpreted as the domain of all r and theta with r bigger than square root of 2. So the domain is, you know, take a radius with square root of 2. It's everything outside of that. Okay, and now I forgot the Jacobian, which is an R. So don't forget the Jacobian. Beyond that, there's nothing interesting going on here. This is integral 1 over r squared, and then cosine theta minus sinus theta with a 2 theta dr. And again, it is worthwhile to think about which one you do first, because cosine theta and sinus of theta over a whole period, both of them have integral 0. So actually, we get 0 without having to compute the r integral. So if we did r integration first, we would just waste a bit of energy, but get the same answer, of course. Yes, questions? No questions, then we move on with number 5. Compute the length of the curve parameterized by yada yada. So this goes back to the very first lecture, right? The length of so if a curve, you think of t as time, then you differentiate that curve, you get a vector, which is the velocity. If you take the norm of that, you get speed. And if you integrate speed, you get length, right? So the length of the curve, the formula for that is just so in general, for a curve r of t, the length is equal to the integral. So t goes between a and b as always. I don't write that up. So you have the integral, and then you have r prime, norm of that dt. Very easy to remember. In our case, the parameterization is given here in the exercise, right? R is not boldface, but it's T3, T2, and 3T4. So the derivative of that is 3T squared, 2T, and 12T3. Right? Tja, Anders. Ska du ha någonting här nu? Hoppas jag inte.
Ja, klockan 1.
Klockan 1, ja just det. Men jag är färdig innan dess.
Det är den här kopplingen bara som
Ja.
tar en del uppmärksamhet i anspråk.
Okay, so Anders Olofsson kom in här, men det kan vi finna oss i. What was the integration limits? It doesn't really matter. Whatever the integration limits were, there was a mistake in this one. So we get an integral which we cannot solve. 9t4, that's the square of that guy, plus 4t squared, plus 144t to the power of 6 is the thing we're integrating, the t, and then of course we can pull out the t square here. That will give us a t, and then we have 4 plus 9t squared plus 144t to the power of 4. And I think this was supposed to be like I don't know what, but anyways, this is something that we don't find a primitive to this one, so that's why I said it has a bug. But the rest of the solution is, of course, anyway, the key part, the final part of actually computing the number is just knowing your analysis one. So if you make it to this point, you got to write the t in the end. That's still, I mean, then. Yeah, I should write modulus t, but t is a positive number. I'm pretty, let's go back to the exercise here. So t is between 0 and 1, right? So then when I pull it out, I don't need to write modulus. Okay, so that formula is completely natural. A formula which is not at all natural is the one for doing the surface area. So that we have to kind of memorize it almost. It looks a bit the same. So one way to remember it is like this. So this formula, if we have that r of t is just like a graph, so if we're in two variables, and this is t and f of t, right? And the corresponding formula for length is integral from a to b. Or instead of f of t, let me write y, okay? And here I can write x. So x, r of x. Okay. Then the formula here is integral 1 plus y dy dx squared, and then dx, right? That's the formula for arc length. Now, if we have a graph in two variables, so like a surface then, that we can parameterize as x, y, and then c of x, y, where c is the function. So the analogy with what's going on here now becomes pretty clear, because now we have that the surface area is given by the integral over the whatever domain you're interested in, instead of the integral from a to b. But this thing here now looks exactly the same. So you have dc dx, the partial derivative with respect to x squared, and a dc dy squared dx dy. So this is what I lectured last class. Of course, you can always derive this expression from, let me stop sharing. Wait, yeah, okay. There's something in my chat. Okay, there's nothing in each one. So this is more like a memory rule. If you remember this one, then it's easy to remember that one. The real integral formula that we have, of course, is if you have just a general parameterization, so R of two variables, S and T, then the area is given by the integral over some domain norm of dr ds cross product dr dt and norm ds dt. So again, a bit similar to what we have in the length. Well, there's some similarity at least, but right. So here you have this more complicated thing that if you apply it to a graph with this structure, you get out this expression here. But that then requires a bit of computation. Okay, so anyways, we need to know or remember this formula, the one here, yeah. So if we have that formula, solving the exercise is pretty straightforward. So let me go back to share. So here's the function, and the domain we're integrating is the unit disk. So I'll flip the camera a bit in this direction and compute over here. So C is now equal to 2, 1 minus x squared minus y squared, and D is equal to unit disk. So then the C dx is equal to half goes down, keeps that guy, but then there's a minus 2x coming, and then, all right, so it's going to be this. dc dy looks analogously. Right? And this gives us this thing. Is equal to, okay, so now we have to square both of these guys. So we get square root 1 plus 4x squared, and down here I have 1 minus x squared minus y squared, and then I have plus 4y squared, 1 minus x squared minus y squared. And then we do a bit of geometry here, so, no, not geometry, algebra. Here I can write this as the denominator as numerator and denominator, right? And then I get a 1 minus x squared minus y squared. And then I have a plus 4x squared and a plus 4y squared. So it's the same denominator in both, right? So at the end of the day, this is square root 1 plus 3x squared plus 3y squared divided with 1 minus x squared minus y squared. Okay. So this is what we have to integrate. And then now we have to do this over the unit disk. So naturally we switch to polar coordinates again. So the area is double integral. So from 0 to 1, 0 to 2 pi, the thing I'm integrating is 1 plus r squared divided with 1 minus r squared, or the theta dr with a 3 here. I mean, now from, I mean, several variables perspective, we're done. This is now down to, can we compute this integral or not? Again, it looks a bit like a difficult one. I can't say off the bat that I know how to get the primitive. So maybe there's a bug in this one too, I don't know. I should take this exam off the curriculum of all the exams that we go through. But anyways, so the main points, I'm not gonna you know, waste everybody's time by trying to find the primitive to this function. It is probably doable somehow, but the several variable calculus is in what we already did. So leading up to this expression, that's what several variable calculus is about. So I'll make sure that there are no very difficult integrals in your exam this year. Questions? You know what, guys, I think the problem is the 2 sitting here, probably that one, because if we don't have the 2, then we get an x and a y here, and then when we solve these 2 guys, the x's and the y's upstairs are going to completely cancel out, and then we get an integral here without the 3r squared, and that can perfectly be solved, because then this guy is the inner derivative of him, and the primitive is easy to see. So that was probably what was had in mind whoever made the exam. Who could it be? Let's not investigate that further to protect the identity of that sorry individual. Anyways, questions? No questions. Okay, so the last exercise is about implicit function theory. Okay. Consider the surface yada yada yada. For most points, this defines C as a function of x and y. Okay. For which points does this fail? So here, this is actually a bit of a trap. Of course, you can use the implicit function theory, right? And then, so how would we solve this with the implicit function theorem? So let's say we have to introduce some functions so that this is the 0 set. So fx, y, and c is equal to 2x plus y3 minus 3yc. So I move the yc's to the other side, because then I can write that my surface is equal to the equation f equals to 0, right? The set of solutions to that equation. And then implicit function theory tells me when this is solvable in a neighborhood of a point on the surface. So if I want to solve for c as a function of xy, I'm interested in knowing when this derivative is not equal to 0, which means that I have to think about minus 3y is not equal to 0, which of course is the same as saying that y should stay away from 0. So if I have a point x, y, c where y is not 0 and it lies on the surface, then I can solve c as a function of x and y locally. But if you, okay, so this is correct. Nothing's wrong with this. It just kind of shows that, well, I mean, it's important to, just because you have these massive theorems, not look at the expression in front of you and just think a bit first, right? Because here, you don't need the implicit function theorem if the equation you're trying to solve is actually solvable, then you just solve it. So a better solution is to note that, okay, if I move this back, my equation is as it was originally posted. And then you can just, if y is not equal to, if y is equal to 0, clearly you cannot solve for c because then c kind of disappears. And if y is not equal to 0, then in the neighborhood you have c equals to 2x plus y3 divided by 3y. So that's explicitly your solution. You don't need the implicit function theorem if you have an explicit solution, right? Jag har bara 2 delfrågor kvar så jag borde vara färdig inom kort. All right, guys, so we have to speed this up. For which points as above can you not solve for y as a function of x and c? Now that's a more complicated one because y, if you think of x and c as fixed variables, there is no way we can solve this. Well, there's some way, but we get a third order equation and we don't have the tools to solve that. There is some algorithm made by some Italian in the 15th century, but it's not taught anywhere these days. So we don't, it's very hard to see what's going on. So then we have to rely on this. So when can we solve this? Now it is when the f dy is not equal to 0. And looking at our equation system, that's the same as saying 3y squared minus 3c should be not equal to 0. So c should not be equal to y squared is the condition. Yeah? And then, all right, so those are the points where, or at least the implicit function theorem does not guarantee that we can solve for y as a function of c. And show that the answer is parameterized by this curve. Well, that's pretty straightforward. So I can set c equals to t. So I just changed the name of the variable basically. Then here I get this equation system tells me that, okay, so this, if I want points where it's not, where implicit function theorem doesn't tell me that I can solve, then I'm clearly getting y. Sorry, yeah, all right. So I'm doing it the other way around. I'm setting y to be equal to t, and then this equation here tells me that c is equal to t squared. And then at the end of the day, we want f of x, y, c to be equal to 0, which gives me an equation for x that I can solve. So that equation would be 2x plus t3 from y3 equals 3 t3. Okay, yeah, and then I move this t3 to the other side. I get a 2, I cancel the 2, so I get that x should be equal to t3. So then we see that all the points on this surface where you can't solve or you potentially can solve at least y as a function of x and c are lying on this curve here, parameterized like this. That was it. So the remaining three were much faster than the first three. But indeed, the whole exam was a bit messy. We'll give you something more clean. Okay, so we see each other tomorrow at 8 again. So I'll just close now because there's another lecturer waiting. So thank you for today and goodbye.